So, any questions from last time? What we have studied so far is the transformation of a vector from one coordinate system to another coordinate system. And we did this from the vehicle to the body, from the vehicle fixed coordinate system to the body fixed coordinate system. Basically from the northeast down coordinate system to the body fixed coordinate system, and vice versa. We have also found out that if you rotate a coordinate system 3 times around 3 axes, by 3 rotations you can go from any coordinate system to any other coordinate system. And for that you need 3 angles to define these rotations. We use these 3 angles for 2 things in flight mechanics, the way I explained it last time. One is to find the orientation of the vehicle in space, basically the attitude or the angular position of the airplane, but also to transform a vector from one coordinate system to another. In our case, we looked from vehicle to body or from body to vehicle. Okay? What we're going to do today is we're going to apply the same concept on transforming a vector from the wind fixed coordinate system to the body fixed coordinate system. We can do that, right? I mean, these are, again, 2 coordinate systems. Both are attached at the CG of the aircraft. So you could actually, again, transform a vector written in the wind axis system and transform it to the body fixed coordinate system. It will be the exact same idea as we have done previously. So let me just start. So what we're going to do next is we're going to do a transformation of a vector from the wind fixed coordinate system to the body fixed. And I can't emphasize this enough. We are not transforming the vector. The vector is the same vector. We are just changing the coordinate system on that thing. All right? So, how did we define the wind fixed coordinate system? This is my airplane, right? I would just say that this is the center of gravity, and let's say we are looking for the velocity of the relative velocity of the local air. And in aerodynamics, we used to call this V infinity, right? Basically, the air that is moving relative to the airplane towards the airplane. Every now and then someone asks me, if the airplane is in space and there's no wind, where is V infinity? It's not that. The atmosphere might be still and you might be moving towards the air, and from the point of view of the airplane, you will see the air is coming towards you. Right? In reality, the airplane is moving towards the air, and therefore there's a relative velocity that the air will see from the front because of your movement. Okay? So if the atmosphere is still, then it actually means that the airplane is actually moving towards V infinity with this vector, and this is the velocity of the aircraft with respect to Earth, thinking that the Earth and the atmosphere are one and the same, which means they are not moving relative to each other. In other words, there's no wind. Okay, this is what we call wind, right? We call atmosphere is still, means the atmosphere is, the air is not moving with respect to Earth. If the air starts moving with respect to the Earth, we call it wind, right? We call it wind. This is what we call wind, if the air moves with respect to Earth. I mean, in a very broad sense now talking. Okay, so if the airplane is moving in this direction like that, so this would be V infinity on still air, still atmosphere. I will call this still atmosphere. and I would say that there is no wind. Okay, no wind. It's a still atmosphere and there's no wind. Okay? So, what is the x-axis coordinates, the wind fixed coordinate system? How do we show the wind fixed coordinate system? Well, this is how we show it. If you recall, xw would be in the direction of v infinity, right? Zw would be in the symmetry axis of the aircraft, and it would be 90 degrees. And Yw would be such that it forms a right-handed coordinate system. Now, this is a right-handed coordinate system, right? This is how I established the wind fixed coordinate system. First, xw points towards v infinity. Zw is 90 degrees, but is in the symmetry plane of the airplane. The symmetry plane of the airplane, I think we mentioned that before. It's this thing, if this is your airplane, so this would be the symmetry plane. Okay, so it is in the symmetry plane, and Yw is 90 degrees. Okay, so now this is a 2D picture, of course. This is a two-dimensional picture. Okay, now you might also look at this same picture from above, right? The airplane might look like this now. And maybe V infinity is not necessarily in the symmetry plane of this airplane, but V infinity might be actually coming slightly from the side. I mean, you don't see that in this picture. You see what I'm saying? Because it's a 2D picture. Maybe V infinity has an angle like this with the symmetry plane of the airplane. So, plotting the same picture from above would look like this. V infinity would be xw would be pointing towards V infinity, okay? Zw would be in the symmetry plane, which will be, it would be 90 degrees into the plane, okay? It would be into the plane, Zw would be into the plane, and Yw would look like this. You see, that would be 90 degrees, and Zw would be into the plane because of this V infinity is with an angle. Okay? So these are the options that we really have when we have V infinity like this. Okay? It would look like this. Now let me give you another example. Let's say the airplane is like this. Okay? And V infinity is coming like that. So, which direction would be xw? Xw would be like that. Zw would be in the symmetry plane, and Yw would be like that. Could this ever be happening, that V infinity is coming from the top? I mean, not in steady flight maybe, but during maneuvers it could. I mean, look up here. Look up here. This is my airplane. The airplane doesn't always fly like that. It could be doing something like that. Now V infinity coming is momentarily at least coming from the top. What if the airplane is doing this? Look up here. The airplane is doing this. Where is V infinity? At the side, right? This would be V infinity coming from the side if you're flying like that. This is V infinity. Where is xw? Xw is like that now. X body is still here. You see? What if the airplane is falling backwards? Where is V infinity? Coming from the back. Okay? So V infinity is not always this pretty picture here. Okay? It's not always this one. So you have to understand, always points towards V infinity. Okay, so what do we want to do? We want to take a vector, any vector, and we would like to transform it from the wind axis system to the body fixed coordinate system. Okay, so what am I proposing? I'm proposing this. I'm proposing, let's find a vector written in the body fixed coordinate system, but I'm looking for the transformation matrix from a vector that was originally written in the wind fixed coordinate system. So I'm looking for the transformation matrix, and the transformation matrix would be called LBW, right? L, V, W. That's what we would call it, because that's a transformation matrix from vehicle to body. Or alternatively, I might be looking for this. I might be looking for that. XW, YW, ZW, LW, B, XB, YB, ZB. And we know LBV is equal to LWB over -1, which is also equal to LVB transpose. We have shown that the transformation matrices are all inversions are equivalent to the transpose of the same thing. Okay? Good. Okay, so where do we start? This is how we start. We are going to make transformations like we did before. Okay? So we are going to make 3 transformations, X, W, Z, W. Okay? We are first going to transform around the z-axis. Okay? First rotate around the z-axis. Rotate around ZW axis by an angle of minus beta. I will tell you why there is a minus. It's just a convention. We can say beta, but we call it a minus beta. I will tell you later why. And we obtain a new coordinate system that's x1, y1, and z1. Okay? You have the vector written in a new coordinate system, just rotated around ZW. Okay? And the second rotation will be, what's our convention? We rotate around Z and then around Y. Good. Y1 axis. That's our convention. By an angle alpha. And this one will give you, I claim, YB, ZB. So note that I'm not rotating around Z. No rotation around X because you will see in a minute that every time we rotate, make these 2 rotations, you will reach the new coordinate system. So basically you will coincide you will coincide with only 2 rotations. Only 2 rotations will be enough in this case. And you know why that would be? Why is it enough to only rotate in 2 angles but not in 3? Because you would think that XW, I mean the wind fixed coordinate system, and X body, they're arbitrary in space. So you need 3 rotations typically. But in this case you need only 2. Why would that be? First of all, can they be arbitrary? They are not arbitrary because we constrain ZW to be in the symmetry plane of the airplane. So we already constrain ZW. ZW cannot be anywhere. ZW has to be in the symmetry axis. So once you make that constraint, then you will see that 2 rotations will be enough. I will show you also as in examples now that you will see in 2 coordinate rotations you'll be done. So no rotation in X needed. I mean, typically you would need it, but in this case you don't need it because we constrain ZW. Okay? Because ZW is constrained, you don't need the 3rd rotation. Okay? So basically, then I can write it like this: XW, YW, ZW. It is 2 rotations. Okay? Rotation number 1 will be no, I'm sorry, go the opposite way. X body, Y body, Z body is equal to L2 alpha, it's a rotation in Y, L1 minus beta, that would be this one, and XW, YW, and ZW. Right? So if you look at this part here is X1, Y1, Z1. I mean the intermediate coordinate system, right? I mean this one here. The intermediate coordinate system, it's right here. So you get this. All right? So let me write down these numbers, and then maybe we talk a little bit more about what they actually mean. First of all, any questions up to this point? I mean, this point might not be intuitive. The X rotation might not be intuitive immediately, but when I show you a few examples, you will see what I mean. But you understand this thing, right? It should be simple, very similar to what we did last week. Any questions? Okay. So let me write this thing down then. It will look like this, X by B, Y B, Z B. The rotation here, this one is around the x-axis, the y-axis. So it will be like this, cosine alpha 0 minus sine alpha 0, 1, 0, sine alpha 0, cosine alpha, times this one with a minus beta, cosine minus beta, oops, sine minus beta, 0 minus sine minus beta, cosine minus beta, 0, 0, 0, 1, xw, yw, zw. Okay? And this one here, if you multiply these two, you would get L, B, V. Okay? So if you would go the opposite way, if you would go from X body to wind axis, you would be doing this. You would first go the opposite now, right? You would first, if you want to go the opposite direction, which means you want to go from here to here, you would first need to rotate this around the y-axis by a minus alpha, right, the opposite way, and then from here to here, rotate it around z1 in this case, by plus beta, and you would obtain at the wind axis coordinate system. So it would look like this, alpha 2 minus alpha, and L1 beta, right? So it would go in the opposite direction. So this would be the other coordinate transformation. Okay, so let's look at an example. Any questions up to this point? I will give a few examples so we understand this. Okay, so it's kind of straightforward, I believe, but still, let me give you a few examples. Let's think of an airplane that has the following situation here. This is the airplane. I'm going to make it a little exaggerated so that we can see it a little better. And let's say this is V infinity. Make it with a big marker. Let's say this is V infinity. Okay? So X body is like that. This is X body. And therefore this is Y body. I'm a Z body. Okay? Coordinate system V infinity is coming from here. Let's look at the same airplane from the top. Same airplane from the top. And let's say V infinity is coming from here. Okay. So that means this is still x body here. And this is y body. And this is here y body, of course. Okay? Same airplane. Okay, and therefore this direction here, this would be xw, right? This would be yw, and in this case this would be xw, right? And this one would be zw. Does that make sense? And this part you should really know by now, really by heart. If you don't, really go back to 3 weeks before and rework everything. Okay? All right-handed coordinate systems, everything fine, the definitions are okay. X body, y body, z body fixed to the coordinate system, x body is looking towards the nose, and xw is pointing towards V infinity. Now this is the same picture, this is the same airplane. So from which direction, I will try to get up now. Good. From which direction does V infinity really come? Let's say this is my airplane. Can you see my marker? Which direction does V infinity really come? From the side it looks like this. V infinity is coming from here. Which means the airplane is either doing this, right? Or the picture is kind of skewed and the picture looks like actually like that. So anyway, V infinity is coming from here. That's one picture. The other picture is, if you look from the top, V infinity seems to be coming from the side, you see, according to this. V infinity is coming from the side. So rotate the picture, V infinity is coming from the side. So it is both coming from the bottom and from the side, which means in 3 dimensions, V infinity is something like that. A little bit from the side, okay, and a little bit from the bottom. So V infinity is actually like that. Not like this, not like that, but it's like that in 3 dimensions. You understand that? Okay, so it's like this. So therefore, xw is pointing in this direction. xw is pointing in this direction. Okay? So we would like to move xw to x body. How do I rotate this? So the first thing we do is we rotate xw in the zw direction. So we rotate it like that and bring it to the symmetry axis. Okay? xw is here, zw is in the symmetry axis, so we rotate around the symmetry axis and move xw into the symmetry axis. So we do this. This is the beta rotation. Okay? We'll get this. First rotation around zw, xw is here, zw is here, rotate around zw, you can imagine zw in the symmetry axis, rotate around zw and you move the coordinate system here. Now you have a new intermediate coordinate system, x1, y1, z1. Okay, it's now like this. This is the coordinate system. The second rotation will be around y1, and y1 is pointing now this way. So you rotate around y1 by an alpha, and you coincide finally with x body. Okay? X body from x1 to x body. X body, x1, and rotate it to the side from here to here, you get the wind axis coordinate system. This rotation is by a minus beta, and the second rotation here is by a plus alpha. Does that make sense? So I don't need the third rotation. I don't need a rotation around x, you see? This is already the x-axis. I don't need a rotation because I already coincide with x body. 2 rotations are enough. 1 rotation around z, one rotation around y, we are already at the body fixed coordinate system. The reason why we don't need a third rotation is because ZW is already in the symmetry axis, so I don't need to do anything in the x-axis. I just rotate around Z, and this moves over here, and then it moves over here, and that's it. And that's your body fixed coordinate system. Is that clear? Okay. Good. So I make two rotations. One rotation is alpha, one rotation is beta. So let's look at the angles. Well, this angle here, move this around. This angle here has a name, and this angle here is called beta. Okay, and that's a plus beta. And that is what we call the side slip angle. Okay? And this one here, and this is typically a positive alpha, if you show it like that. This is not good. Do it like this. Sorry, this doesn't look good. Okay, this is what we call the angle of attack. And going down like this, when V infinity is blowing from below somewhat, let's just say, we call this a positive angle of attack. Okay, so if the airplane is like this, and V infinity is coming from below like that, and this is X body, and this is Y body. So this angle we would call a positive alpha, and that's a positive angle of attack. So this is this angle, it's a positive angle of attack. We call it angle of attack, and that's a positive one. You understand that? Now, all these things that I've been explaining now, in terms of the rotations from the wind to the body, actually help us define the two aerodynamic angles, which are obviously very important, right? The angle of attack and the side slip angle. Now, the angle of attack, everybody has probably seen this picture here, where you have a V infinity and you have the chord line, right? And then in between, this is called an alpha. It is the angle of attack. Angle of attack creates lift, and so on and so forth, the whole story. But we never, maybe you did, but in most classes, you always look at the 2D picture. You never look at the picture where V infinity is not exactly in the plane of the airplane. In this case, it is not in the plane of the airplane. In fact, V infinity is not like this. It is coming with an angle. So in this case, where is alpha? The angle of attack. You can find alpha by rotating this coordinate system by the side slip. Now this is angle of attack. Just like in the Euler angles. When I ask you where is phi, where is theta, where is psi? When I have an airplane like this, where is psi? You first rotate around phi, you come back with theta. Now this is psi. Same thing over here. If you have a V infinity that looks like this, so where is alpha? You rotate around beta. This is alpha, angle of attack. Where is beta? Rotate back. This is beta. This rotation is beta. What is that rotation? You take XW, rotate around ZW until you reach that plane here, the symmetry plane. That angle here is beta. That is what we call a side slip angle. And then this one here is what we call an alpha. Of course, if there's no side slip, then this picture is perfect. That picture over there is perfect because this is your alpha, no side slip. Then you can plot that picture. It's a 2D picture. There's no beta. Same thing with that picture. You know, If there's no alpha, then yes, of course, this is beta, right? This is beta. All right? But if it's a 2D thing, this is beta and this is alpha. Now, if V infinity is coming this way, look up here. V infinity is like that. What do? Rotate around beta, come to the symmetry axis of the airplane. This is beta, and this is your alpha. Is this a positive or a negative alpha? Negative. Why do we call this a negative alpha? We call this a negative alpha because of our convention that we use in aerodynamics. A positive alpha is giving us positive lift. A negative alpha is giving us something else, probably negative lift, I mean in the direction that we don't like, downwards, right? So from an aerodynamics point of view, we like to call this a positive alpha, which does not match our sign convention, because YB is in this direction. A positive rotation of YB would be up, not down. Take YB, you see YB? Want to go up, this would be a positive angle rotation, but you go this way. So we call the negative one a positive alpha, and this is because of aerodynamic convention. We don't like to call this a negative alpha. We don't want to say a negative angle of attack is giving us positive lift, right? So we say a positive alpha is giving us lift, so this is a positive alpha. So it's the definition of alpha, how we define it. But look at beta. This is what we call a positive beta if it comes from the right. Now this makes sense because ZB is in this direction. It's in the symmetry plane. So you take your thumb. So this is a positive rotation, see? This is a positive beta in XYZ, in the body axis system. If you look up here, in the body axis system, Y should have been up, not down. So there's a mismatch in the definitions, because if you look at the YB, in order to get V infinity, you need to go in the negative direction. However, here, in the body fixed coordinate system, you get ZB, and you need a positive rotation around ZB, and you get positive beta. You understand that? This is positive. This should have been positive up, but down is positive. So there's a mismatch. Therefore, that's why you see the negative number, the negative alpha, or the negative beta, vice versa, how you look at it, you get that difference here. You get a minus beta here and a positive alpha here. You might ask, why is this negative and why is this positive? The reason is because from a sign convention, we are using a wrong convention in one of them. You can argue which one is correct, which one is wrong. But we say when you go from the body fixed coordinate system, the YB is in the opposite direction. So therefore, the definition of alpha is a little skewed, is not really correct. So we are using still a positive alpha for the downward rotation. And therefore, we have a positive here and a negative here. And if you go the other way around, actually you see this. You see? You want to go from body to wind axis. You need a negative rotation in alpha. Okay? And then you need a positive rotation in beta. This is kind of wrong because a positive rotation in Y would be going up. But as from the definition of angle of attack, we don't like that. We like to call this one a positive alpha. Understand? That one we call a positive alpha. That's why you have that mismatch. Is that clear? Any questions? Yes, please. Yeah, yes.
But if we use right-hand rule to first picture, blue arrow shows negative value for this picture. So I believe blue arrow might be wrong.
No, that's what I'm trying to explain.
Yeah, I understand.
Yeah.
If you check the values after giving them a real values, if you put right thumb to the YB,
yes.
Blue is negative. Blue will have negative value.
That's right. That's right. But this will be a negative value. It will be like minus 16, for example.
Yes.
Right? But we call this still plus 16. Are you confused with this alpha here or with this plus alpha or?
No, just
Okay. Do you? Okay.
direction of arrow.
Okay. You mean this? The blue? Do you mean this direction here?
Yeah.
So this would be a positive rotation, but it is not a positive rotation. It is a negative rotation. The blue arrow. It's a negative rotation. You see. But this will be a positive number. This will be some 20 degrees, for example, although it's a negative rotation. Okay, that's what I'm trying to say. Okay, so what else? What else? Good. Why is this rotation so important? Well, it is important because it gives us the definition, a clean definition of angle of attack and of side slip. Now, how do you define angle of attack? How would you define angle of attack? I bet a lot of people would just plot this picture here and say this is angle of attack, isn't it? But now we need a very precise definition. We have a precise definition. It is the rotation of V infinity around ZW, and then that new angle is the angle of attack. So to be precise, angle of attack, we would define it like this. It is the angle between the angle between the body x-axis and the vector which is obtained by projecting the local air velocity V infinity onto the aircraft's symmetry plane. And this is a proper definition of angle of attack now. It is the angle between the body x-axis and the vector which is obtained by projecting the local air velocity V infinity onto the aircraft symmetry plane, which also means rotate xw towards the symmetry axis. You might want to write that down too. Or rotate wind axis around ZW by minus beta, then it is the angle between x1, the intermediate x, and b1, and xb. Okay? So that's the definition of angle of attack. Where in this definition, alpha is angle of attack, we sometimes write it like this, and beta is what we call the side slip. Okay, that's the side slip angle. Any questions? Definition should be very clear now. Yes?
Of course, we define angle as
line is not on the XP plane?
Yeah, that's a question that comes up every now and then. When you have an airfoil, let's put it that way, okay? When you have an airfoil, then this is your chord line, and if you consider this airfoil as your body, then this is also your body fixed coordinate system, and it is a chord line.
So we are not always considering the whole airplane?
No, let me just start. If this is just an airplane, if this is a 2D airfoil, okay? If this is a wing, you typically do the same thing. You look at the chord line, okay, and somewhere at the CG, or if it's a 2D thing, then there's no CG, but you put it somewhere along the chord line and say this is your X body. Now, if you have an airplane, and let's say you have a wing, and let's say the nose of the airplane and the chord line are not exactly the same, right? That's your question. Okay. Now, we can talk, in this case, of two things. We can talk, let me put it this way, and let's say this is V infinity. We can talk of two things. We can talk of the angle of attack of the airplane, or we can talk of the angle of attack of the wing. So, which one are we talking about? Which one do we want to talk about? So you might want to think of this whole airplane as a lifting body. I mean, the lift is not only produced by the wings. I mean, this whole body, this whole geometry is producing lift and drag. So yes, there is a chord line, but you might want to think of this whole system, this whole structure as a shape that looks a little funny, but it tries to imitate an airfoil or a lifting body. So if you ask me, there is no wing, fuselage, this and that. There's not really a separation anymore. This is one big structure that is creating lift and drag. So I would like to talk of the angle of attack of this big structure. But, and therefore I will call this one alpha of the airplane. But if you would like to talk about the wing only, then you tell me, you say, now I'm talking about the wing only, and therefore the chord line is my reference axis coordinate system, and therefore this is what I call alpha of the wing. Okay, I mean, we can talk about this. Again, I would claim that if there's a side slip, then you rotate around ZW, and then this one here would be alpha. You first rotate around beta, and then this one would be alpha. If you're talking about the airplane, then it's this one. As of now, for now, I'm talking about the airplane, the full airplane. Therefore, for me, the airplane's angle of attack is this. Okay? But as I said, someone might come up and talk about the angle of attack of the wing. Then it's something else. Understood? So as long as we are clear with what we're talking about and the definitions, we are okay. The angle of attack of an airplane in this class and in many places, we define as I defined over there, the projection of V infinity onto the symmetry plane, which means a rotation around this, and X body is this one. That's it. Another thing you might think of is if the nose and the angle of attack, the mounting of the wing, if they are very close, I mean this angle is not usually very high, right? If they're very close, you could move this X body a little bit up and down, and that's your new body fixed coordinate system. Because you're fixing the body fixed coordinate system. When I say towards the nose, it is not really a very precise definition, is it? Where is the nose of the airplane? I mean, it is somewhere out there. But as long as we fix it, we all know where X body is, we can still talk of alpha. Understood? Because if you think about it, alpha, beta, body fixed coordinate system, vehicle carrier, and all this, these are all things that we are making up. Right? We are calling certain angles alpha, certain angles beta, that we are making up. When you build an airplane, it's not It's not like a rule or a natural phenomenon that there is an alpha or something. These are definitions that we are making. As long as we are clear with the definitions, I think we are fine. Okay, so let's give a break. Be back in, let's make it not too long, please, okay? Let's make it 50, okay, exactly 50.